Today I will be discussing Lab 3, looking at the orbit of a black hole. The objective of this lab was to find the mass of a black hole and to model the motion of a star that is being acted on by the black hole. To do this, we were given only the motion data of the star, which is just the position over time. So the result of this lab was that given the mass of the star and the position of the black hole, we were able to determine the mass solely from the motion data. This experiment makes use of Newton's second law in the form of the momentum principle, which states that final momentum equals initial momentum plus the net force times the change in time. Using momentum, we also have to account for the fact that the motion of the star is circular. In circular motion, you can state that the momentum at a specific point is equal to the magnitude of the momentum at that point times the direction of the momentum at that point. Taking the derivative of this, we can see that the change in the momentum over the change in time is equal to the change in the magnitude of the momentum over the change in time times the direction of the momentum plus the momentum times the change in the direction over the change in time. Looking at this equation, we can see that the first half of it is the parallel component of the change in momentum, and the second part is the perpendicular component. We can simplify this by stating that the momentum at any given point is equal to the parallel component of that momentum plus the perpendicular component of that momentum. Because the net force is equivalent to the change in momentum over the change in time, we can change this formula to say that the net force at any given point is equal to the parallel component of the net force plus the perpendicular component of the net force. We are going to use this relationship in our code to determine the mass. The last major model that we are going to use in this experiment is Newton's law of gravitation. This law states that the magnitude of the net force on two objects because of gravity is equal to the gravitational constant times both masses divided by the distance between the two squared. Looking at our code, we can see that the only initializations that we have to make are the star's mass, the black hole's position, and the delta t, which is the equivalent of 1 year in seconds. After the program imports the star data CSV file, which is just composed of the position data over time, we can see that the code calculates the velocities between each of the positions and stores it into a new list. This list will be used to determine the momentums at each time step and then the net force at each time step. The loop of this program determines the initial momentum and the final momentum, then converts that into delta p, and divides that by delta t to get dp dt, which is then set equal to the net force. After finding the parallel component of dp dt, we can then find the perpendicular component by subtracting it from the total dp dt, and then Fnet is set equal to each component of dp dt. After computing each component of the net force, we create arrows that depict each component on the model of the star. When the code is finished running, we can see that it computes the mass of the black hole using Newton's law of gravitation. If we run the code, we can see the motion of the star as it moves around the black hole, and each arrow depicts each net force, the total net force, the parallel net force, and the perpendicular net force. For the what does it mean question, we were asked to determine the difference between the net force and each of its components and the change in momentum over change in time in each of its components. The net force and the change in momentum over change in time are said to be equivalent. However, the net force is more of a quality, whereas the change in momentum over change in time is able to be measured. For the what-if question, if we replace the black hole with a black hole of a different mass, then the motion data will not be the same. This means that any black hole placed in the same position, acting on the same star in the same way, will have the exact same mass. In conclusion, the mass of the unknown unseen object could be determined based off of the motion data of the nearby star and the position of the object.